Okay, hi everyone. It's a pleasure to be here. So thank you very much to the organizers for inviting me. I'm going to talk today about mostly some work that I did recently at the University of Freiburg in Germany, even though I've now moved about 6 months ago to the University of Cambridge, looking at dynamic strength and fragmentation and how it relates to impact cratering. And because I'm first, I get the prerogative of saying impact cratering is really important. It's really the dominant surface process on solid planetary bodies. This isn't immediately obvious when you look at the Earth, because there's a lot of other processes on Earth that obscure the Earth's impact record. But when you look at other planetary bodies, this is Mercury, the Moon, Mars, and Charon, it's pretty much the dominant surface process. And one part of the impact cratering process that's particularly important is the strength of rocks. The reason why strength is important is that it can control the size of an impact crater. This is particularly important for laboratory scale impact experiments and the things that we use to benchmark everything that we know about larger scale cratering that we're not able to achieve. So it affects the size of craters, and also it affects whether planetesimals may or may not be disrupted by an impact event. So this is certainly something very important for the processes that were active during the early solar system. Okay, so, but the thing is about rock strength is that it's not a static property. I mean, probably everyone is fully aware of the fact that rock strength depends upon pressure, but also it's very rate sensitive as well. So this is a compilation of data from Kimberley et al., where they developed a universal scaling relationship that shows how uniaxial compressive strength varies as a function of strain rate. Basically, it's this sort of exponential function of this normalized stress is related to normalized strain rate to some exponent 2/3. So basically, what this is essentially that above strain rates of about 10 to 100 per second, rocks have a strong dependency on, rock strength has a strong dependency on strain rate. Why does this happen? Well, essentially it's due to the behavior of fractures. So in brittle materials, when a single fracture under slow deformation can grow fast enough to accommodate the deformation, but at very, very high strain rates, a single floor isn't able to grow fast enough to accommodate the loading. So you activate an increasing number of floors, increasingly strong floors, and that leads to the increase in strength in the rock, but it also leads to fragmentation of the rock mass. So as you increase the strain rate, you increase the amount of pulverization of the sample. And this also has some pretty important effects on the impact cratering process, because essentially the fragmentation that occurs during impacts controls the properties of planetary materials and planetary surfaces. As an example of this, the moon is pretty pervasively fractured to a depth of about 20 kilometers, and it has porosities of up to about 20%. And that's entirely due to impact processing and impact fragmentation. Another thing is that fragmentation controls the size of ejector fragments from impacts. And this is quite an important thing because impact ejector can produce secondary impact craters, which affect our ability to date planetary surfaces. But while fragmentation is really important, there's actually no general theory that allows us to predict how fragment sizes vary as a function of strain rate. There are theoretical models that predict how fragment sizes work during tensile failure. This is the so-called expanding shell problem, which is shown on the left-hand side here. And essentially, this is a rather unique case. But what all models of this tend to predict is that at high strain rates, fragment size goes with strain rate to the power of -2/3. And this is sort of this tail end. All of these models kind of predict more or less the same kind of thing. But compressive fragmentation is really rather different to tensile fragmentation. I mean, as we know in general, compressive brittle failure is rather different to tensile brittle failure. So that there was a video of a split Hopkinson pressure bar experiment on westerly granite. That's uniaxial compression essentially that's causing a really rather different kind of fragmentation to the expansion of a ring. So the work I'm going to talk about is about, basically we were trying to investigate what strain rates are required to produce rate-dependent effects in rocks, and then how does this strength dependency affect the impact cratering process. And we were also interested in how the process of fragmentation works. I mean, hypothetically, the ideal situation that we're trying to get to is, could you say something about the conditions of failure if you were to look at the products? As geologists, could you look at the fragment size of a fault rock somewhere or in an impact crater, and could you use that to tell you something about what the strain rate was at failure? Okay, to do that, we did some rock mechanics experiments. We used a hydraulic loading frame and a split Hopkinson pressure bar. The hydraulic loading frame achieved strain rates about 10 to the minus 6 to 10 to the minus 4 per second, while the split Hopkinson pressure bar achieves much higher strain rates at about 10 to 1000 per second. I'm not going to go into too many details about how the split Hopkinson pressure bar works, but if you do have any questions, please do let me know at the end. We've investigated a variety of different rocks, crystalline rocks, both with and without anisotropy. We've investigated porous sedimentary rocks and also sort of non-porous equivalents of those rocks. So for a sandstone, we have a quartzite, and for a limestone, we have a marble. So cutting to the chase and looking at the results, this is the results of a series of experiments where essentially what we can see is that every single lithology that we investigated does indeed follow this scaling relationship of Kimberley et al. And the main control on this relationship is the characteristic strain rate, epsilon dot naught, which takes a value of somewhere between about 150 and 300 per second. That characteristic strain rate is the strain rate at which strength is double the quasi-static value of strength, which means that strength increase due to dynamic effects sort of starts to matter above about 15 to 30 per second for all of these rocks. Okay, which are essentially strain rates that would happen during impact cratering events and also other kinds of dynamic geological processes. Just to show I'm not covering anything up with logarithmic scales, here it is just shown on a linear scale, just to show the variety of the data that we have. And I should also say that in our lab in general, we have also been looking at tensile strength. So this is a summary of some tensile strength results. But for the most part in this talk, I'm going to be talking about the results of compressive failure. The general result of these tensile experiments is that the characteristic strain rate for tensile failure is lower than the characteristic strain rate in compression. Basically, it's easier to get dynamic strength increases in tension than it is in compression. So we also looked at the fragment sizes that are produced from these experiments. What I've done here is I've plotted up sieving results, and I fitted all of the distributions to Weibull distributions, not necessarily because Weibull distributions have any theoretical grounding. You could use a variety of other analytical distributions to fit this data. But I just chose Weibull distributions because it fits the data quite nicely, and it has a certain appeal due to the fact that at small fragment sizes, it simplifies to a power law distribution, which is used quite commonly in the study of fault rocks. And the most important thing to spot here, of course, is that as strain rate increases, as you go from these purple to yellow colors, you see increasing amounts of fine material. You have increasing fragmentation with increasing strain rate. And this can be expressed somewhat more simply if we just plot the average fragment size for each of these experiments against strain rate. And what we see is that all of these lithologies follow power law relationships between strain rate and fragment size. The exponent of that is somewhere between -2/3 and -3. But it wouldn't exactly be fair to go about directly comparing this to some of the tensile fragmentation models, because we haven't kind of attempted to scale this model in any way, or scale this data in any way. So after a little bit of sort of trying to do some dimensional analysis, basically we found a way to normalize this data such that everything collapses approximately onto a single relationship. We normalize the strain rate by the characteristic strain rate of the material, simple enough, and the characteristic fragment size that we use to scale fragment size, we use something based on sort of a modeling exercise by Camacho and Ortiz to define a length scale that describes the distance, the communication distance between flaws in the material. And basically what we find is that everything does collapse onto a power law relationship. So here we have all of this data on the solid line. These are all of the non-porous rocks, where essentially we have an exponent of about minus 1.9 for all of these non-porous rocks. And then all of the porous rocks collapsed onto a relationship that's parallel to that, has the same exponent, but it has a slightly different constant. So what that ultimately means is that the constant of this relationship K appears to be some function of porosity or some property that's closely related to porosity. But we don't have enough porous rocks to necessarily be able to refine exactly how K is a function of porosity. And what this scaling relationship is describing is how fragment size varies as a function of strain rate during uniaxial compression. Okay. So we've got an idea for how fragment size might vary as a function of strain rate. We also thought about how fragment shapes might vary as a function of strain rate. I started off by doing this by hand picking all of the fragments that you got from all of these experiments. I got to about 2 millimeters size, and then I got bored. So after hand picking down to that size, we then had to employ a different technique for the finer fragments, where we sort of randomly scattered material. So we got two different methods, and I was analyzing what the circularity of these particles are. One would be a perfectly circular particle, 0 would be a perfectly non-circular particle, i.e. a straight line. And then we're also looking at axial ratio, which is 1 over the aspect ratio, which is because it gives you a value between 1 when it's perfectly equal aspect and 0 where it's infinitely not equal aspect. Essentially what we find here, these are the large fragments, the fragments larger than 2 millimeters, is no change in the fragment size as a function of strain rate. So here we have 4 different lithologies. I didn't do any more of this because I started realizing that there was no difference essentially when I found that. So with increasing strain rate, there is no change in either the circularity or the aspect ratio of these fragments. And in fact, exactly the same thing is true when you look at the finer fragments as well. There is no, the fragment shape is independent of strain rate, and it also kind of appears to be fairly independent of lithology as well. So this was a bit disappointing at first. I kind of wondered why is this the case, given that we know the fragment size is very definitely changing. So I had to think about how you could go about randomly fragmenting an area. I looked at 3 different potential algorithms for sort of theoretically how you can fragment areas and what effect that might have on fragment shapes. This is a so-called random lines algorithm that you can see here, where you're just putting in a random line and you're increasing your number of fractures and you produce fragments. You're randomly fragmenting an area. This may not necessarily be the most natural way to fragment an area. This is another algorithm, which is a random line segments, where essentially every single time you put in a new line, you are you define that it cannot cross any other line that already exists within the fracture area. And then this is another method, which is called Voronoi segmentation, where you randomly fragment an area. All 3 of these are essentially just random ways of fragmenting an area, but what I wanted to see was what happens to fragment shape as when you change these algorithms, and what happens as a function of strain rate. And in this case, what we're thinking about is that strain rate is somewhat related to the number of lines that you put in. The number of fragments that you create, the number of fractures that you put into your area is somewhat analogous to the strain rate, because you increase the strain rate, you increase the number of fractures. And the thing that we see for most of these algorithms is that there's no relationship between fragment shapes and the number of lines, i.e. the strain rate that you might expect for random fragmentation. So what this really suggests is that the process of dynamic fragmentation is in many sense a random process. It's driven by the randomness of the flaws that are in the material. So I kind of want to come to a sort of a conclusion here of saying that dynamic strength increase does definitely occur in rocks with characteristic strain rates of about 150 to 300 per second, which means it is significant at strain rates greater than about 15 to 30 per second. Fragment size can be expressed as a power law function of strain rate. This expression shown here. But I suppose I should stress that this is only for uniaxial compression. One thing that we're really quite uncertain about is how to expand this to confined stress states. Truly triaxial stress states may produce a different fragmentation relationship to what we're seeing here. Fragment shape, on the other hand, is independent of strain rate. So that means we can't really say a lot based on the shapes of fragments that we see in fragmented rock masses about the process itself. At this point, I would go on to talk about what effects this really has on the impact cratering process, but I haven't quite got that far, to be honest. But what I can show you at least is that this is a process that really should matter. So here, everything that is colored from purple to yellow is in compression, and it is experiencing a strain rate that's greater than about 10 per second, above that threshold where strength-related effects should matter. Everything that's dark gray is at very, very high pressures, so it's ductile normally, and everything that's light gray is in tension, I should say. So all of this colored material should be experiencing dynamic strength effects, but we don't consider that in any model. So this numerical model that I've used is not considering that strength is a function of strain rate. There is currently no model that currently predicts that. So that's something that I'm currently working on. I would love to have shown results, but I only got my code to compile yesterday, so I don't actually have any results. But this is essentially the implementation that we're looking at. This is essentially it's not quite more Coulomb space, but it's shear stress and pressure. And this is how strength will vary as a function of strain rate in this model. At that, thank you all for listening. And if you want to read any more, please take a look at these papers.